Welcome back to our online video lectures on medical imaging. In the last video lecture, we were discussing about image gradients, and now we will continue our discussion from there. So we discussed that a gradient, for example, for a 2D image has two components. That vector has two components at every pixel, derivative in the x direction and derivative in the y direction. Then you could compute the magnitude of it by taking squares of those derivatives and taking sum them up and taking a square root of it. You can also find out the orientation normal to the edge. So that's the direction of the gradient. So gradient would be always perpendicular to the edge. And then we were discussing about how do you compute these derivatives in x and y directions. For that we discussed about how you do it. For example, derivative in the x direction, it's exactly same for y, except that now where you have x plus 1, there you have y plus 1. Okay, you just change the name of the variable. That would give you the directions in the y. And then we took couple of different derivatives in the x direction. One is the central difference and forward difference, backward difference. These were the names for what we computed. And if you are taking the central difference based derivative computation, you would then be having a mask which is symmetric. So that's one typically you might use for computing the derivatives. While you compute the gradients, essentially you need to compute edges in the horizontal direction and edges in the vertical direction. Those are not the only ways to compute your horizontal and vertical edges. So in addition to the gradient operators that we have discussed so far, there are other ways of computing the gradients, and there are instances where you may want to compute the gradients in a particular orientation. That's also is possible. If you look at very early works where they are trying to find out these gradients, is for example, this is referred to as Roberts edge detectors. This is for detecting the diagonal edges. Assume that your edge is like this, okay, then you expect differences in intensities here. So that's again you will be subtracting the intensities of these two pixels. That's to find out an edge like this. So suppose if you consider this x, this is for example 45 degrees edge. And similarly, if you want to find out the all edges that have an angle of minus 45 degrees, this is something you could use then. So you are trying to take a difference between these two pixels. Okay, now anyways you rarely would be using Roberts. More common ones are Privet and Sobel, and perhaps you would usually go for, it is quite common that you would be going instead for Sobel, but let's still see the both and you should be clear with the both. Now you want to find out, let's say, horizontal edges. You could think of it in this manner. You want to compute the gradient that we discussed so far, but for that the horizontal and vertical edges you could compute them using this Privet and Sobel as well. For example, assume that you have an edge here. Okay, so what would happen if it is a horizontal edge in this row and in this row? Compared to that, there is a transition of intensities. So what you are going to do now, you take minus 1 minus 1 minus 1 here, 1 1 1 here. Essentially when you are correlating with this mask, okay, this is equivalent to subtracting these intensities, right, with this. This is at y plus 1 and this is at y minus. So you could see that this index would be y plus 1 here and this index would be y minus 1. So that's essentially, if you take this value, right, the one which I circled there would be equal to f of x comma y plus 1 minus f of x comma y minus 1. Okay, similarly you could write for the other also. So this is a horizontal edge, right? In other words, in terms of the gradient, this is a vertical gradient because edge is perpendicular to the gradient. And similarly you could make a similar interpretation for computing a vertical edge. This is your vertical edge, okay, and then x plus 1 minus x minus 1, similarly that, but with varying y values here. So while computing at this central pixel, the horizontal edge or vertical edge, you are here looking it into neighboring values also. Had it been the earlier definition of derivatives that we are looking at, there would be only these two values. Now in addition, you are taking a neighborhood as well here, the next pixels also, there also you have -1 -1 -1 -1. Similar is the case for the computing vertical edge or horizontal gradient, in other words. This is as far as the pivot gradient operator is concerned. Now if you look at Sobel, what it does is in very similar lines, but it gives more weight to the intensity differences coming at the central pixel. So now here if you see, double the weight of the difference that you get here gets twice the difference that you get at the other two pixels. So this is -1 -2 -1 1 2 1 for horizontal edge, or in other words vertical gradient, and here -1 -2 -1 1 2 1 here. So an edge, vertical edge is here, so from here to here there should be, the differences should be there, so that's why you are doing it. So just take a closer look into it. This is very intuitive and it should be very clear to you as well. Now there could be special cases where you want to find out edges which are there at 45 degrees, similar to what we have seen at Robert. Okay, that also is possible. Here this is again for privet. This is the edge you would like to figure out. This is the edge you want to find out here. Similarly Sobel, you want to find out an edge here, or you want to find out this edge here. So you could see here, these are your central pixels anyway. Okay, now what you are doing here, 1 -1 1 -1 1 -1, these are the diagonal edges. Same, now this edge you want to find out, so you are going to take differences at the pixels of, this is -1 1 -1 1 and -1 1. Similarly in case of Sobel, double the weight would be given to the central pixel, so you could see here 2 -2 and then 1 -1 1 -1. Similarly here this is -2 2 -1 1 -1 1. Okay, hope this is clear to you. This is a very special case. You might not use it if you are using these operations in as a part of computing your horizontal and vertical derivatives of your gradient. You will not come to this, but in a special case where you would like to find out an edge, as I mentioned, which is at ±45 degrees, then you could use the above privet or the below Sobel, depending on whether this is +45 degrees edge or -45 degrees edge. Now for the sake of simplicity, let's come back to 1D again, and this is again a very commonly known thing to you. Finding out a derivative would give you the information of presence of an edge, as derivative would tell you where there is a sudden change. But suppose there is some noise that got added to an image, where ideally this is a constant intensity here. Okay, the original intensity, assume that this is how you expect the intensities to be constant, but what happened, noise got added and there is a slight variations happening here for this, and similarly here. Now for us intuitively, we know that since there is a big jump here, this is where you have a strong edge. But if you simply do the operation, particularly f of x plus 1 minus f of x by 1 to compute the edge, this is what you would be getting there. That will not work well. Why is it so? Because these all small values, although they are changing it, so x plus 1 and x, when you compute this, the derivative at those spikes, at those noisy points, is pretty high. So what to do here? Dou by dou x of f of x, if you compute it, you can't really figure out that there is an edge here which got dumped along with other spurious false edges. So what you have to do is, you simply do a Gaussian, first a Gaussian kernel you apply here, Gaussian smoothing you apply here, or some other smoothing also works well. So in fact, if you closely observe and look into the privet and Sobel, that in fact has in a way both smoothing and edge detection put together. Okay, anyway we are not going to look into the derivations of Privet and Sobel. We use them with just an intuitive understanding of them. We'll go ahead and keep using them. So here assume that you do now on this, instead of directly applying a derivative, you first convolve it with a Gaussian kernel, right? Then how do you get the result? Anyways, you are for a reason you are missing this part, because this kernel, when you are at these points, you need to do some padding here. So you are just considering a valid region, so you will start from here. So this is what you would be getting. Now this H convolved with F, okay, I could call it a correlation also, because that's a symmetric mask. Now if I take derivative of it, then I would nicely get here a high value of jump here at this edge. Okay, so while you are looking at an edge, it's better you convolve it with a Gaussian, and then followed by it you use your edge detector. Could be a simple central difference scheme for computing the derivative. Assume that you have n points here while you are doing it. Let's again look in just 1D. You have n points there. So this convolution you have to do at n, all the n points, you get a result. So I leave it to you to figure out what would be the order of complexity while doing this. And then on that again, to assume that the part you are losing here because of that is negligible, and still assume that I would consider the resulting image is also n. Okay, now again on top of it you are doing one more convolution, right? So two times a convolutions with the data of size capital N. Is there any better way than doing this? Now you would realize that since this has an associative property, you could exploit that property in order to do it in a very simple way. How do you do that? So essentially what we are doing is dou by dou x on H convolved with F. That's what we are doing it. Now this could be written as dou by dou x of H convolved with F. So you are taking derivative of your Gaussian kernel, and simply with that you are going to convolve F. So this is your Gaussian kernel. You all know this would be the derivative of it, and you just do a convolution over just data sets of n points here. That's directly with this, rather than doing two separate convolutions with data size of capital N. Then you would arrive at the same result. Out of those two convolutions you have to do, you can get rid of it. Instead of all you need to do is, instead of using this mask, you use that, and it is sufficient if you are doing just at n points one convolution. Now the next point will be when there is a edge. Okay, you would see here a peak in the first order derivative. Now suppose if I am taking a second order derivative, what would happen then? So you could figure out here that this would result in now at the edge a zero crossing. So if you are using the first derivative, you look at where the peak is, and if you are taking the second derivative, you simply look at where zero crossing is there. That would still tell you where the edge is. So that's exactly what you could observe here. So what is it that we have to now do here? You want to take dou by dou x of the whole thing. Again you use associative property. This I could write it as dou by dou x of dou by dou x of H whole thing convolved with F. So take one more derivative of it. What will that give you? That's what would give you this shape. Okay, inverted Mexican hat, that's what it is usually referred to. You rotate, in case of 2D, how it would be, you simply rotate that, and then it's an inverted Mexican hat. Then if you invert it, it looks like a Mexican hat in 2D. So that's how it is referred to. All you need to do now is, even to find out the second order derivative, one convolution or equivalently a correlation, if you are doing it, that's good enough here to compute the second order derivative. And when you are computing second order derivative, If you want to look at edges, you simply look at zero crossings now. That would give you where the edge is. If you are using first order derivative, then you look for local maximas. That would give you where the edge is. So as I mentioned, that's in case of 1D. In case of 2D, your Gaussian, you started with a Gaussian. How does this Gaussian would look like? So you have the center of this Gaussian here. Okay, 0.09, 0.02, 0.09, 0.02. Same in this. So it will further reduce here. You want a gradient. So now you could take derivatives in both x and y. So if you are doing it one way is 1 minus 1. Okay, that's derivatives in the x direction. And you do now derivatives in the y direction as well. You could do that. So this is a surface plot. Okay, if you are multiplying here instead of 1 minus 1, if you are doing it, let's say, depending on your coordinate convention, whether you considered y as here or y as in this direction, it would, the order would change. But anyways, this is something that you would be getting. So you could see here you are plus and minus, so that's why you could see bright here, dark here. Similarly for the y direction, this is bright and this is dark here. Okay, so those are the derivatives of the Gaussian. Hope it is clear to you. Now let us take a look at how the second order derivative would look like for a 2D image. So for that, let's first find out a discretized version of it. Let's say I want to find out dou square in the x direction. I want to find out the derivative, second order derivative, which would be dou square f by dou x square. So that would be equal to, I could write it as dou by dou x of dou f by dou x. We already had looked at the expression for it. What is that? Let's take here the forward difference expression for it, which would give us f of x plus 1 comma y minus f of x comma y. We want to find out derivative with respect to x. So you have took the function value at x plus 1 comma x. Now how could you write this now? Dou by dou x of f of x plus 1 comma y minus dou by dou x of f of x comma y. Now let's try to, for a given pixel, let's try to restrict to the extent possible to just x plus 1 and x minus 1. Okay, so using those, suppose if I want to find out dou by dou x of f of x plus 1 comma y, how can I write that? You use, for example, then I could use x plus 1 and a pixel behind that, right? So I could go this notation. So how could I write then? F of x plus 1 comma y minus f of x comma y minus of. Now for this dou by dou x of f of x comma y, I could either use the forward difference or backward difference. So let me use now here, there are different ways you could write it, but let me use this f of xy minus, since I have used here backward difference, let me use the same here, x of x minus 1 comma y. So what is this value? F of x plus 1 comma y minus 2 times f of x comma y plus f of x minus 1 comma y. This is my dou square f by dou x square. So that's exactly the expression that you would see here, right? Similarly, I could write for dou square f by dou y square. These are the second order derivatives in x and y. Now I am sure you all know the Laplacian operator, which is a combination, or more precisely a summation of the second order derivatives both in the x and y direction. So that's equivalent to dou square f by dou x square plus dou square f by dou y square. You already got the expression for dou square f by dou x square. Similarly, you replace with just simply x with y, you would get the expression for, and y with x, you get expression for dou square f by dou y square, and you sum them up both, then that would give you the expression for the computation of the Laplacian for at a given point. So what would be this expression is, let's look at here. So basically at the center you have -4 here, okay, that's what you could see here, f of xy. Then you have all these four terms put together, x plus 1y, x minus 1y, xy plus 1 and xy minus 1. If I write them in case of a kernel or a mask, so I have -4 here, then 1 1 1 1 here. Okay, this is referred to as 90 degrees isotropic Laplacian mask. Okay, 90 degrees because you are looking at all the pixels which are there at 90 degrees, and isotropic, even if you rotate by 90 degrees this would remain same. That's why it is referred to as 90 degrees isotropic Laplacian mask. Now there is something else also which is called as 45 degrees isotropic mask. We are not going into the derivation of it, but let's go through an intuitive explanation of it. Now if I want to make it 45 degrees, why only take difference with respect to this? Let me put values for these also, 1 1 1 1 here. Okay, and then so if you see, all these masks would give you the summation would be equal to 0 here. One simple check you could think of why this is the case is, consider a uniform region where your Laplacian should be 0. So unless the sum of this mask is getting 0, this won't happen. Okay, that's one simple check that you could do. So that way when you are keeping all ones here, so what's the entire value here? This is equal to 1 2 3 4 5 6 7 8. So you make this to -8. So that's exactly the mask you have here. So this is called as 45 degrees isotropic 2D Laplacian mask. Okay, you call it as for convolution or be it correlation, it's not going to have any difference because that is symmetric mask, is it not? So Laplacian is essentially encoding the second order derivatives both in the x direction and y directions by computing dou square f by dou x square plus dou square f by dou y square. Okay, as it is looking both in the x and y direction, it is taking second order derivatives. So any sudden transitions in the intensities in any direction would be nicely captured and encoded by this Laplacian operator. So this is also used for enhancing the edges. How exactly is this used for enhancing edges? We are going to see it shortly, but I hope so far it is clear before we move there. Suppose you want to highlight sudden transitions in intensities. All you need to do now is you compute the Laplacian operator and add it to the image. Okay, since the Laplacian is having high values at those pixels where there are sudden transitions, it should give you a better result. So that's exactly how image enhancement is done. By the way, magnitude wise, even if I take negative, that should not cause any problem with this. So if I take a negative of this, this would be the just I'm making the sign changes here, that's what you should be getting. And then you consider this, you add to that the original image. For the time being you just focus on this part. Okay, so you compute the Laplacian, and at the xy pixel you just add to the original intensity. So that's what the mask you have it is like this. Similarly, if you are using 45 degrees isotropic, this is how the mask would look like. Once you understand this concept, there is nothing much to remember here. You could do it starting from the scratch here, and then you are able to quickly figure out what exactly are these masks on your own at any given time. Now let's come for an example on how you could use this information. This is now explained here using a whole body scan. Assume that this is a PET scan and you want to detect diseases such as bone infections and tumors. So essentially you want to highlight the bones in the entire image, so they have a clear edges. For example, find out them when you are doing some Laplacian operation, then you would like to increase that. What are the typical issues that you would get in the regular conventional way of the raw image that you would be getting out of your scanner? Will have in the first place a narrow dynamic range, and then noise content is very high. So to deal with them, what is done is, this is the bone scan that you are going to get. Now you compute a Laplacian, okay, and of course after computing the Laplacian you make it to 0 to 255 as well, and then you add the both, okay, these two images you add. Then you could clearly see in this image bones are very enhanced. At the same time you could also see regions where the noise is also getting enhanced. So to deal with that, what you would do is, Sobel, if you notice there is some smoothing happening there, you would get a slight blurring which is you won't be getting with Laplacian. So you keep this for now as it is. In addition, what you are going to do now is, for this image you apply Sobel edge detector, okay. So that means you do both x, y. You can take square root of x square plus y square. Usually you won't do that. You take instead square absolute value of x and y, as that other operation is computationally expensive anyways. So you are getting this Sobel. And now, as I mentioned, there could be blurring effect in Sobel, okay. So what you would do is, this Sobel you will not right away use it, but you would use Sobel to get rid of the noise. So how you would do that? This Sobel you further smooth it if you want, so that the region of your Sobel expands to its neighboring pixels. Say for example they have used an 5 by 5 filter there, and then notice here, this is original plus Laplacian. You are going to create a mask with it, okay, and that mask original plus Laplacian into the smoothed label. That's what you are going to do. On one side Laplacian is enhancing very well even as small changes. Sobel is helping you to get rid of the noisy regions, and you are using both together here, and thereby getting the regions of where you have bones or real edges, and then that you are adding to your original image and getting an enhanced image there. And of course after that they are further applying a gamma correction here, okay, the range of intensities that you would like to see, further you could improve the contrast. So this is one example where you could see application of gamma correction, application of edge detection, where you are using the first order derivatives, and then Laplacian, all put together to get an enhanced image. You notice in the first image you could hardly see anything here, okay, in the legs and other places. On the contrary, you could see the bones in the legs very clearly, and even the outer contours of your body. But of course one has to be careful here while you are doing these operations, because the scanner, whatever output you are getting, has a physical phenomena to back it up, and why you are getting that. All these operations also you should make sure that you are getting the right image, okay. So with that, let's conclude our discussion of image enhancements in the spatial domain, and from the next class onwards let's move on to image enhancements in the frequency domain, okay. Thanks for watching. See you in the next video lecture. Bye. Take care.